On the morning of September 14th, 2015, something happened that had never happened before in the 4.5 billion year history of our planet. A whisper from the universe, traveling for 1.3 billion years across the cosmos, finally reached Earth. It was the sound of two black holes, each roughly 30 times more massive than our Sun, spiraling into each other and colliding at half the speed of light. The impact converted 3 entire solar masses into pure gravitational energy in 0.2 of a second. For roughly 20 milliseconds, this collision released more power than all the stars in the observable universe combined, and we almost missed it. The signal that arrived that morning changed the length of a 4-kilometer laser beam by less than 1,000th the width of a single proton. To put that in perspective, imagine stretching a measuring tape from Earth to Alpha Centauri, our nearest neighboring star system, 4.2 light years away. Now imagine detecting whether that tape got longer or shorter by the width of a single human hair. That is the level of precision we are talking about. That is what it took to hear the universe speak for the first time. This is the story of how we built an instrument sensitive enough to detect the impossible. It is the story of a 100-year prediction, a 50-year quest, and the 3 minutes that changed everything we thought we knew about the cosmos. But to understand why this moment mattered, we need to go back, way back, to a patent clerk in Switzerland who was about to turn physics upside down. In 1915, Albert Einstein completed his general theory of relativity. It was, by any measure, one of the greatest intellectual achievements in human history. Newton had described gravity as a force, an invisible pull between masses. Einstein said no, gravity is not a force at all. It is the curvature of space-time itself. Massive objects do not pull on each other. They bend the fabric of the universe, and everything else simply follows the curves. Think of it like a bowling ball placed on a stretched rubber sheet. The ball creates a depression, and if you roll a marble nearby, it curves toward the bowling ball, not because the bowling ball is pulling it, but because the marble is following the curved surface. Now scale that up to stars and planets and galaxies, and you have Einstein's universe. But Einstein's equations contained something else, something he was not entirely comfortable with. When you disturb space-time, when you accelerate massive objects, the disturbance ripples outward like waves on a pond. These ripples are gravitational waves. They travel at the speed of light, stretching and squeezing space itself as they pass. Einstein published his prediction of gravitational waves in June of 1916. But here is the thing. Just 4 months earlier, in February, he had written to the physicist Karl Schwarzschild saying, and I quote, "There are no gravitational waves analogous to light waves." He was not even sure his own prediction was correct. And honestly, even if gravitational waves existed, Einstein thought detecting them was basically impossible. The effect was just too small. Gravitational waves from even the most violent cosmic events would stretch and squeeze distances by an almost immeasurably tiny amount. By the time they reached Earth, you would need to detect changes smaller than an atomic nucleus to find them. Einstein essentially said, "Good luck with that," and moved on. But the story gets stranger. In 1936, 20 years after predicting gravitational waves, Einstein changed his mind entirely. He and his assistant, Nathan Rosen, submitted a paper to the Physical Review titled, "Do Gravitational Waves Exist?" Their conclusion was no, they did not. Einstein and Rosen claimed to have found a mathematical singularity in the equations that proved gravitational waves were impossible. The editor, John Tate, did what good scientific journals do. He sent the paper out for peer review. An anonymous referee, later identified as Howard Robertson, wrote a 10-page critique identifying fundamental errors in Einstein's math. When Tate forwarded the critique, Einstein was furious. This was the first time in his career that a paper had been rejected. He wrote an angry letter, withdrew the manuscript, and vowed never to publish in Physical Review again. And he did not, except for one letter in 1952. But here is the twist. Robertson later explained the error to Einstein through a mutual colleague, Leopold Infeld. The singularity Einstein had found was not physical. It was a coordinate singularity, like how longitude becomes undefined at the North Pole. It was a quirk of the mathematical framework, not a feature of reality. Einstein quietly corrected the paper. When it was eventually published in the Journal of the Franklin Institute, the conclusions were completely reversed. Gravitational waves, Einstein now agreed, definitely exist. So even the man who predicted them was not sure. Even the greatest physicist of the 20th century got confused by his own equations. That should tell you something about how hard this problem is. For the next 40 years, physicists argued about whether gravitational waves were real, not mathematically real. Everyone agreed the equations produced them, but physically real. Could they actually carry energy? Could they actually affect matter? Or were they just mathematical ghosts, artifacts of the equations with no physical meaning? The debate came to a head in January of 1957 at the University of North Carolina at Chapel Hill. About 40 physicists gathered for what became known as the Chapel Hill Conference on the role of gravitation in physics. Among them was a young physicist who had registered under a pseudonym because he thought the whole field of gravity research was frankly a bit embarrassing. His name was Richard Feynman. He signed in as Mr. Smith. Feynman was already famous for his work on quantum electrodynamics. He thought gravity research was underfunded and underappreciated, but also kind of a backwater. Still, he attended the conference, and during the discussions, he presented an argument that would settle the debate once and for all. Imagine, Feynman said, a rigid rod with beads that can slide along it freely. The beads slide with just a little bit of friction. Now imagine a gravitational wave passes through. The wave will stretch space in one direction and squeeze it in the perpendicular direction. The beads, being free to slide, will move relative to the rod. That friction will generate heat. The heat is energy. That energy had to come from somewhere. The only possible source is the gravitational wave itself. Therefore, gravitational waves carry real physical energy. They are not mathematical ghosts. They can do work on physical objects. The sticky bead argument, as it became known, convinced the skeptics. Hermann Bondi, who had been on the fence, became a convert and later popularized the argument in his own writings. After Chapel Hill, the question was no longer whether gravitational waves existed. The question became, how do we detect them? Sitting in that audience was a physicist named Joseph Weber. He left Chapel Hill fascinated, and he decided he was going to be the one to find them. Weber was a genuine pioneer. In 1965, he built the first gravitational wave detector at the University of Maryland. It was not a laser interferometer. It was a resonant bar detector, a massive aluminum cylinder about 2 meters long, 1 meter in diameter, weighing roughly 1,400 kilograms. The idea was simple. A gravitational wave passing through would make the bar vibrate ever so slightly at its resonant frequency, about 1660 Hz. Piezoelectric crystals attached to the bar would convert those tiny vibrations into electrical signals. Weber built 2 of these bars and placed one at Maryland and one at Argonne National Laboratory, about 1,000 kilometers away. In 1969, he announced that he had detected gravitational waves. He claimed to have found about 24 coincident events, signals appearing in both detectors simultaneously. By 1970, he was reporting over 300 events. The physics community was electrified. If Weber was right, this was one of the greatest discoveries of the century. Other groups immediately began building their own detectors to verify his results. IBM built one, Stanford built one, Bell Labs, Oxford, Cambridge, universities and national laboratories around the world all tried to replicate Weber's findings. None of them found anything. By 1974, the consensus was clear. Weber's detections could not be reproduced. Richard Garwin at IBM calculated that if Weber's claimed detection rate was correct, the universe would have to convert all of its energy into gravitational radiation in about 50 million years. That was physically impossible. Something was wrong with Weber's analysis. A physicist named David Douglas discovered errors in Weber's computer program. At the 5th Cambridge Conference on Relativity in 1974, Weber faced aggressive public confrontation. His funding was cut. His reputation was in tatters. But here is the thing about Joseph Weber. He was wrong, but he was not crazy. The principle behind his detector was sound. It was just nowhere near sensitive enough. The gravitational waves he thought he was detecting were simply not there. The real signals were thousands of times weaker than what his instrument could measure. Weber never gave up. He continued working on gravitational wave detection until his death in 2000. And today, one of his original resonant bar detectors sits on display at LIGO Hanford, a tribute to the man Kip Thorne calls the founding father of gravitational wave detection. The date of LIGO's first detection announcement, February 11, 2016, happened to fall on the anniversary of Weber's death. His widow, astronomer Virginia Trimble, sat in the front row. While Weber was building bars, other physicists were thinking about a completely different approach. What if, instead of waiting for a gravitational wave to make something vibrate, you used light itself to measure the stretching and squeezing of space? The idea goes back to the early 1960s, but the person who really figured out how to make it work was a physicist at MIT named Rainer Weiss. Weiss was born in Berlin in 1932. His family fled Nazi Germany when he was a child, eventually settling in New York. He studied at MIT, earned his PhD in 1962, and became a professor there. In the early 70s, he was teaching a course on general relativity and realized he did not actually understand gravitational waves well enough to explain them. So he set out to design a thought experiment, a detector that could actually measure them. That thought experiment became a landmark document. In 1972, Weiss published what is now known as the MIT Quarterly Progress Report, number 105, titled Electromagnetically Coupled Broadband Gravitational Antenna. It sounds dry. It was anything but. In that paper, Weiss identified every single noise source that would plague gravitational wave detection: seismic vibrations from the ground, thermal vibrations from molecules in the mirrors, quantum fluctuations in the laser light, and he designed a laser interferometer that could in principle overcome all of them. The basic concept is elegant. You split a laser beam in two. You send the two beams down perpendicular arms, bounce them off mirrors at the far ends, and bring them back together. If the arms are exactly the same length, the light waves recombine perfectly. But if one arm is slightly longer than the other, the waves arrive out of phase and create an interference pattern. Now here is the key insight. A gravitational wave stretches space in one direction while simultaneously squeezing it in the perpendicular direction. If you have two arms at right angles, a passing gravitational wave will make one arm longer and the other shorter. That difference shows up in the interference pattern. Weiss built a prototype with arms just 1.5 meters long. It could not detect anything, but it proved the concept worked. He spent the next 3 years trying to convince anyone who would listen that this approach could succeed. One of the people he tried to convince was Kip Thorne. Thorne was a theoretical physicist at Caltech, one of the world's leading experts on general relativity. Born in 1940 in Logan, Utah, he became one of Caltech's youngest full professors at age 30. His textbook Gravitation, co-authored with Charles Misner and John Wheeler and published in 1973, trained an entire generation of relativists. It is over 1,200 pages long and weighs nearly 6 pounds. Physicists call it the Bible of General Relativity. When Weiss first explained his interferometer concept to Thorne, Thorne was skeptical. He spent 3 years evaluating whether it could actually work. By 1975, he was convinced. He became one of the project's strongest advocates. Thorne brought something Weiss could not provide. He had connections at Caltech, one of the most prestigious physics institutions in the world, and he had ideas about what kinds of astrophysical events could produce detectable gravitational waves. Colliding black holes, neutron star mergers, supernova explosions. Thorne calculated the expected signals, giving experimentalists targets to aim for. In 1979, Thorne recruited a Scottish physicist named Ronald Drever to build an experimental program at Caltech. Drever had been doing gravitational wave research at Glasgow University since 1970 and had built early interferometer prototypes. He was brilliant, innovative, difficult to work with, and absolutely essential to the project's success. Drever invented or co-invented several key technologies that LIGO would eventually use. Most importantly, he was one of the developers of the Pound-Drever-Hall technique, a method for stabilizing laser frequency that became crucial for achieving the required sensitivity. By the early 1980s, there were 2 competing groups working on laser interferometer gravitational wave detection: Weiss at MIT and Drever at Caltech. In 1984, the National Science Foundation pressured them to merge into a single project, LIGO. The Laser Interferometer Gravitational Wave Observatory was born. It was not a happy marriage. Weiss and Drever had very different personalities and very different ideas about how to proceed. The collaboration was contentious from the start. In 1994, a physicist named Barish was brought in to save the project. Barish was born in 1936 in Omaha, Nebraska. He was not a gravitational wave physicist. He was a particle physicist who had managed large experiments at places like Fermilab. He knew how to run big science. When Barish arrived, LIGO was in trouble. The National Science Foundation had funded construction of 2 detector sites, but reviews expressed serious doubts about whether the project could ever achieve its goals. The management structure was chaotic. Personality conflicts were derailing progress. Drever was forced out of the project in 1992, before Barish even arrived, a casualty of the dysfunction. Barish transformed LIGO. He instituted professional management practices. He replaced unreliable argon gas lasers with solid-state lasers. He created the LIGO scientific collaboration, a framework for sharing data and coordinating research among hundreds of scientists worldwide. Most importantly, he pushed through approval for advanced LIGO, an upgraded detector that would be roughly 10 times more sensitive than the initial version. That factor of 10 in sensitivity does not sound like much, but here is the thing about gravitational wave detection. If you double your sensitivity, you can see objects twice as far away, but the volume of space you can observe goes up with the cube of distance. So doubling sensitivity means observing 8 times more volume, which means detecting roughly 8 times more events. A factor of 10 in sensitivity means a factor of 1,000 in observable volume. Initial LIGO, which operated from 2002 to 2010, never detected a gravitational wave. It achieved its design sensitivity, but that sensitivity was only good enough to observe neutron star mergers out to about 8 megaparsecs, roughly 26 million light-years. The nearest large galaxy cluster is farther than that. Advanced LIGO would change everything. Construction of the initial LIGO detectors took years. There are 2 sites, one in Livingston, Louisiana, about 50 miles east of Baton Rouge, one in Hanford, Washington, on a decommissioned nuclear reservation. The sites are separated by 3,002 kilometers, roughly the distance from New York to Los Angeles. Why 2 sites? 3 reasons. First, coincidence detection. A real gravitational wave will hit both detectors. The maximum time difference between arrivals is about 10 milliseconds, the time it takes light to travel between the 2 sites. Local noise, things like nearby traffic or small earthquakes, or even people walking around, affects only one detector. If you see a signal in one detector but not the other, it is not a gravitational wave. Second, source localization. The time delay between when a signal arrives at each detector tells you something about where it came from. With 2 detectors, you can narrow down the source to a ring on the sky. With 3 or more detectors, you can triangulate to a much smaller region. Third, veto power. Any signal with a delay greater than 10 milliseconds is automatically ruled out. It cannot be a gravitational wave traveling at the speed of light. Each LIGO detector is an L-shaped interferometer with arms 4 kilometers long, 4,000 meters. So long that the curvature of the Earth, nearly 1 meter over that distance, had to be accounted for during construction. GPS-guided precision leveling kept the laser beams perfectly horizontal. The arms are not open air. They are vacuum tubes, specifically 1.2 meter diameter tubes made of spiral welded stainless steel, pumped down to 1 trillionth of atmospheric pressure. That is 10 to the minus 9 torr, a better vacuum than outer space. The entire tube system contains 10,000 cubic meters of vacuum, making it one of the largest high vacuum systems ever built. It took 40 days of continuous pumping to achieve, with the tubes heated to 170 degrees Celsius for 30 days to drive out residual gas molecules. Why such extreme vacuum? Because even a tiny amount of air would scatter the laser light and ruin the measurement. A single molecule in the beam path creates noise. At the ends of each arm sit the mirrors. These are not ordinary mirrors. They are 40 kilogram cylinders of ultra-pure fused silica, polished to a smoothness of about 1 nanometer, roughly the size of a few atoms. The surfaces are so perfect that only 1 in 3.3 million photons is absorbed rather than reflected. The rest bounce back toward the beam splitter. The mirrors hang suspended in a quadruple pendulum system, 4 stages of isolation, each one filtering out ground vibrations at different frequencies. The final stage uses fused silica fibers thinner than a human hair, tapering to just 0.4 millimeters in diameter. These fibers are phenomenally strong and have very low mechanical losses, meaning they do not vibrate much on their own. The whole suspension system weighs 360 kilograms, but the mirror hangs almost perfectly still, isolated from the constant shaking of the Earth by a factor of 10 to the 11th, 100 billion. Earthquakes happen all the time around the world, small ones every few minutes somewhere. Without this isolation, LIGO would be completely blind. Now, you might wonder why we need 4-kilometer arms. The signal we are trying to detect is a change in length of about 10 to the minus 18 meters. Would shorter arms detect a smaller change? Actually, no. The fractional change in length is what matters, and that is the same regardless of arm length. But longer arms mean the absolute change is larger, which makes it easier to measure with light. Even 4 kilometers is not really enough. So LIGO uses a trick called Fabry-Perot cavities. An additional partially reflective mirror sits near the beam splitter in each arm, creating a resonant cavity. The laser light bounces back and forth about 300 times before exiting, effectively increasing the arm length to roughly 1,200 kilometers. This also builds up the laser power inside the arms, from about 200 watts input to approximately 100,000 to 750,000 watts circulating. Think about that. Nearly a megawatt of laser power bouncing around inside these cavities, all to measure a change smaller than a proton. Initial LIGO operated from 2002 to 2010. It achieved its design sensitivity, strain, better than 10 to the minus 21. But it detected nothing. The universe, it turned out, was quieter than some optimists had hoped. The team was not discouraged. They had always planned for an upgrade. Advanced LIGO replaced essentially everything. Heavier mirrors, 40 kilograms instead of 11. Better suspension, quadruple pendulums with fused silica fibers instead of single-stage metal wire suspensions. Active seismic isolation, using sensors and actuators to cancel ground motion in real time. More powerful lasers, improved optical coatings. Installation of advanced LIGO began in 2008 and was completed in early 2015. The new detectors achieved a strain sensitivity of better than 10 to the minus 23 at 100 Hz. That is about 10 times better than initial LIGO, which means roughly 1,000 times more observable volume, which means roughly 1,000 times more potential events. On September 12, 2015, Advanced LIGO officially began its first observing run, designated 01. 2 days later, everything changed. The morning of September 14, 2015, was a Monday. At LIGO Livingston in Louisiana, it was about 4:51 in the morning local time. At LIGO Hanford in Washington, it was 2:51 a.m. Both detectors were in what is called engineering mode, a final tuning phase before the official start of science operations. The instruments were running, collecting data, but the team was still making adjustments. At 9 hours, 50 minutes, and 45 seconds UTC, a gravitational wave arrived. It hit Livingston first. 6.9 milliseconds later, give or take half a millisecond, it hit Hanford. That delay is consistent with the speed of light across the 3,000-kilometer separation, coming from a source in the southern sky. The signal was dramatic, a chirp. It started at 35 Hz, swept up to 250 Hz over about 0.2 of a second, then abruptly stopped. 8 gravitational wave cycles, clearly visible above the noise. But here is the thing. Nobody was watching. The detection happened automatically. LIGO uses a system of pipelines, software that analyzes the data in near real time looking for signals. One of these pipelines, called coherent wave burst, flagged the event within 3 minutes. An automated alert was sent to collaboration members. The first human to actually see the signal was Marco Drago, a 32-year-old Italian postdoctoral researcher working at the Max Planck Institute for Gravitational Physics in Hanover, Germany. He was monitoring the low-latency analysis when the alert came in. It was 11:50 in the morning, local time. Drago looked at the data and felt his heart rate spike. The signal was huge. The signal-to-noise ratio was 24, far above the threshold of 8 typically used to claim a detection. The waveform matched the theoretical predictions for colliding black holes almost perfectly. But Drago had a problem. Advanced LIGO routinely performs what are called blind injections, fake signals secretly inserted into the data to test whether the analysis pipelines can find them and whether the collaboration can correctly identify them as fake. These injections are tightly controlled. Only a handful of people know when they happen and what they look like. Was this a blind injection? Or was it real? Drago started making phone calls. Within hours, the collaboration was in an uproar. Emails flew back and forth. The blind injection team was contacted. They checked their records. No blind injection was scheduled. None had been performed. But wait, the detectors were still in engineering mode. What if someone had done an unscheduled injection? What if there was a hardware glitch mimicking a signal? What if this was some elaborate test that only a few people knew about? The collaboration went into detective mode. They examined every aspect of the data. They checked the hardware. They interviewed everyone who had access to the injection systems. They analyzed the signal using multiple independent methods. Over the following days and weeks, they became increasingly convinced this was not a test. This was not an artifact. This was real. The signal came from 2 black holes, each about 30 times the mass of the Sun, spiraling together and colliding 1.3 billion light-years away. In the final fraction of a second, they were orbiting each other at nearly half the speed of light, separated by only a few hundred kilometers. When they merged, they formed a single black hole of about 62 solar masses. Wait, 30 plus 29 is 59, not 62. Where did the extra 3 solar masses come from? They did not come from anywhere. They went somewhere. 3 solar masses were converted entirely into gravitational wave energy. Pure E equals mc squared, 3 times the mass of our Sun, transformed into ripples in space-time in about 20 milliseconds. The peak power output was 3.6 times 10 to the 49 watts. That is 36 followed by 48 zeros. To put that in context, our Sun outputs about 3.8 times 10 to the 26 watts. So this event, at its peak, released energy at a rate roughly 100 billion times greater than the Sun. In fact, for that brief instant, the collision released more power than all the stars in the observable universe combined, 50 times more, according to LIGO's calculations. For 20 milliseconds, 2 black holes outshone everything, and we almost missed it. The collaboration kept the discovery secret for months. They needed to be absolutely certain before going public. They analyzed the data every possible way. They calculated the statistical significance of the detection. The probability of the signal being a random noise fluctuation was less than 1 in 3.5 million. Later analysis pushed that to less than 1 in 203,000 years of observation time. This was not a fluke. On February 11, 2016, LIGO held a press conference in Washington, D.C. David Wrightsey, the executive director of the LIGO laboratory, stepped to the microphone. "Ladies and gentlemen," he said, "we have detected gravitational waves. We did it." The room erupted. Physicists openly wept. A prediction made 100 years earlier by a man who thought it could never be verified had finally been confirmed. We had opened a new window on the universe. The discovery paper, published simultaneously in Physical Review Letters, had over 1,000 authors. The event was designated GW 15914, GW for gravitational wave, followed by the date, September 14th, 2015. But LIGO was not done. On December 26, 2015, they detected a second event. GW 151226 was smaller, quieter, and came from lighter black holes, about 14 and 8 solar masses. But it confirmed that the first detection was not a fluke. Gravitational wave astronomy was real. By the end of the first observing run in January 2016, LIGO had detected 3 confirmed events. The second observing run, from November 2016 to August 2017, detected 8 more. The third run, from April 2019 to March 2020, detected 79. As of late 2025, the total count exceeds 340 confirmed gravitational wave events. The detection rate during the fourth observing run reached roughly 1 event every 2 to 3 days. What was once impossible had become routine. But let me go back to that first detection for a moment, because there is something poetic about when it happened. September 14th, 2015, almost exactly 100 years after Einstein completed his general theory of relativity in November 1915, almost exactly 100 years after he predicted gravitational waves in June 1916. The gravitational waves that LIGO detected that morning had been traveling through space for 1.3 billion years. They were created when multicellular life on Earth was just beginning to evolve. They traveled through the cosmos as dinosaurs rose and fell, as humans evolved and built civilizations, as Einstein worked out his equations and predicted their existence. And they arrived just as we had finally built an instrument capable of hearing them. If that signal had arrived 50 years earlier, we would have missed it. If it had arrived 10 years earlier, initial LIGO would not have been sensitive enough to detect it. It arrived at almost exactly the right moment in human history. Some people call that coincidence. Some people call it luck. Some people call it the universe being poetic. On October 3rd, 2017, the Nobel Prize in Physics was announced. The prize went to 3 people. Rainer Weiss received half for his foundational work on the detector concept. Kip Thorne and Barish each received 1/4 for their theoretical contributions and for bringing the project to completion. The award came just 2 years after the first detection, unusually fast given that Nobel Prizes typically come decades after the discoveries they recognize. The committee clearly felt this was too important to wait, but the prize was bittersweet. Nobel rules allow a maximum of 3 recipients and prohibit posthumous awards. Ronald Drever, who had contributed so much to the technology that made detection possible, had died on March 7, 2017, 7 months before the announcement. Many physicists believe Drever would have shared the prize if he had lived. He had shared the Kavli Prize, the Shaw Prize, and the Special Breakthrough Prize with Weiss and Thorne in 2016. But the Nobel has stricter rules. Drever spent his final years in a care facility, suffering from dementia. He was largely unaware of the detection that vindicated his life's work. By the time the Nobel was announced, he had been dead for 7 months. Science is full of such tragedies. People who dedicate their lives to a goal, but do not live to see it achieved. People whose contributions are essential, but who are forgotten by history. Drever is remembered within the gravitational wave community, but his name is far less known than Weiss or Thorne. I want to tell you about one more detection. It happened on August 17th, 2017, and it changed everything again. GW170817 was different. Previous detections had come from black holes, objects so dense that not even light can escape them. But the signal that arrived on August 17th came from something else. 2 neutron stars. Neutron stars are the collapsed cores of massive stars that have exploded as supernovae. They pack roughly 1.4 solar masses into a sphere only about 20 kilometers across, the size of a city. A teaspoon of neutron star material would weigh about 6 billion tons. When 2 neutron stars spiral together and collide, they produce gravitational waves. But unlike black hole mergers, they also produce light. The LIGO signal lasted about 100 seconds, as the neutron stars completed roughly 1,500 orbits in the sensitive frequency band. It was the loudest gravitational wave signal detected to that point. And then, 1.7 seconds after the gravitational wave signal ended, the Fermi Gamma Ray Burst Monitor detected a flash of gamma rays from the same region of sky. This was huge. Astronomers had long suspected that neutron star mergers were responsible for at least some short gamma ray bursts, intense flashes of high-energy radiation that appear randomly across the sky and last less than 2 seconds. Now they had proof, but that was just the beginning. Within 11 hours, optical telescopes found the source, a point of light in a galaxy called NGC 4993, about 130 million light-years away. The light was strange. It started bluish, then turned red over the following days as the ejected material cooled and expanded. Astronomers called it a kilonova. When neutron stars collide, they fling neutron-rich material outward at significant fractions of the speed of light. That material undergoes rapid neutron capture, a nuclear process called the R process, forging heavy elements like gold, platinum, and uranium. The gold in your wedding ring, the platinum in your catalytic converter, the uranium in nuclear fuel. All of it was likely created in neutron star collisions like the one LIGO detected. This single event produced roughly 10 Earth masses of gold and platinum, 10 times the mass of our entire planet, forged in the collision of 2 dead stars. More than 70 telescopes observed GW170817 across the entire electromagnetic spectrum, from radio waves to gamma rays. It was the most observed astronomical event in history, launching the era of multi-messenger astronomy. But wait, there is more. Because we knew both the distance to the source from the gravitational wave signal and its recession velocity from the galaxy's redshift, we could calculate the Hubble constant, the rate at which the universe is expanding, using a completely new method. The result, about 70 kilometers per second per megaparsec, agreed with existing measurements but offered a fresh and independent check. The neutron star merger also told us something about fundamental physics. The gravitational waves and the gamma rays arrived within 1.7 seconds of each other after traveling 130 million years. That means gravitational waves travel at the speed of light, to within about 1 part in 10 to the 15th power, one of the most precise tests of general relativity ever performed. We also learned about the interior of neutron stars. The gravitational wave signal is sensitive to how neutron stars deform as they spiral together, which depends on the equation of state of nuclear matter at extreme densities. LIGO data constrained that equation of state in ways that decades of nuclear physics experiments could not. One event, 100 seconds, a scientific bonanza that will keep researchers busy for decades. Since that first detection, gravitational wave astronomy has grown from a curiosity into a mature field. The original LIGO detectors have been joined by others. Virgo, a 3-kilometer interferometer near Pisa, Italy, has been operating since 2017. Kagra, a 3-kilometer detector built underground in the Kamioka mine in Japan, the first cryogenic gravitational wave detector, began operations in 2020. It was damaged in the January 2024 Noto Peninsula earthquake, but returned to service in June 2025. LIGO India, located in the Hingoli district of Maharashtra, received formal approval in 2025 and is expected to begin operations around 2030. Adding a detector in the southern hemisphere will dramatically improve our ability to localize gravitational wave sources on the sky. But the next generation of detectors will make even these instruments look primitive. The Einstein telescope is a proposed European observatory that would dwarf current detectors. Instead of 2 perpendicular arms, it would use 3 arms arranged in an equilateral triangle, each 10 kilometers long. The entire facility would be built 200 to 300 meters underground to reduce seismic noise. Each corner would house 2 interferometers, one optimized for low frequencies using cryogenic mirrors, one optimized for high frequencies using high-powered lasers. Estimated cost is about 1.9 billion euros, with first observations targeted for around 2035. The Einstein telescope would be roughly 10 times more sensitive than advanced LIGO, meaning it could detect black hole mergers from essentially the entire observable universe. Every stellar mass black hole merger that has ever occurred, going back to the first stars, would be detectable. Cosmic Explorer is an American proposal for even longer arms, 40 kilometers each. That is 10 times longer than LIGO. With that baseline, Cosmic Explorer could detect binary black hole mergers to redshifts greater than 20, when the universe was less than 200 million years old. Detection rates could reach 100,000 events per year. Construction is targeted for the late 2020s, with operations beginning in the mid-2030s. And then there is LISA. The Laser Interferometer Space Antenna is not a ground-based detector at all. It is a space mission. 3 spacecraft flying in formation in their own orbit around the Sun, trailing Earth by about 20 degrees. The spacecraft would be arranged in an equilateral triangle with arms 2.5 million kilometers long. That is more than 6 times the distance from Earth to the Moon. LISA would detect gravitational waves at much lower frequencies than ground-based detectors. From about 0.1 MHz, this opens up entirely new source classes, supermassive black hole mergers, the collisions of black holes weighing millions or billions of solar masses at the centers of galaxies. Extreme mass ratio in spirals, where a stellar mass object spirals into a supermassive black hole over thousands of orbits, thousands of compact binary systems within our own galaxy, white dwarfs and neutron stars orbiting each other. LISA could even provide early warning of black hole mergers. A supermassive binary might spend thousands of years in LISA's frequency band before the final merger, giving astronomers years or decades of advance notice to point every telescope at the right spot in the sky. The European Space Agency formally adopted LISA in January 2024, with NASA contributing key components. Launch is planned for 2035 on an Ariane 6 rocket. By 2040, we could have a global network of third-generation ground-based detectors, plus a space-based detector listening to completely different frequencies. We will be able to observe gravitational waves from the first black holes that ever formed, trace the assembly of galaxies across cosmic time, and test general relativity in the most extreme environments imaginable. Einstein could not have dreamed of this. He thought detection was impossible. He was wrong about that, and we are all richer for it. Let me come back to where we started. September 14th, 2015, 9:50 a.m., Coordinated Universal Time. Marco Drago, sitting at a computer in Hanover, Germany, seeing a signal that had traveled 1.3 billion years to reach us. What he saw was proof that space itself can ripple, that the fabric of the universe is not static, but dynamic, capable of being stretched and squeezed by violent events half a universe away, that we can build machines sensitive enough to detect those ripples, to hear the universe sing. The signal Drago saw was not just a measurement, it was a confirmation of something deep about the nature of reality. Space and time are not a fixed stage on which events play out. They are participants, shaped by matter and energy, responding to cosmic violence with waves that propagate forever. Every gravitational wave that has ever been produced is still out there, somewhere, spreading through the cosmos at the speed of light. The merger that LIGO detected is still rippling outward, getting weaker with distance, but never completely disappearing. 1 billion years from now, some inconceivably distant civilization might detect those same ripples and wonder about their origin. And every second, new gravitational waves are being created. Black holes are colliding. Neutron stars are merging. Supernovae are exploding. The universe is ringing like a bell struck by countless hammers, and we have finally built ears capable of listening. Before LIGO, all our knowledge of the cosmos came from light. Visible light, radio waves, X-rays, gamma rays, all forms of electromagnetic radiation. Gravitational waves are something completely different. They are not electromagnetic at all. They are ripples in space-time itself, carrying information that light cannot. With light alone, you cannot see black holes. By definition, black holes emit no light. You can only see their effects on nearby matter, gas swirling around them, stars orbiting them. But gravitational waves come directly from black holes, produced when they move, when they collide, when they form. For the first time, we can observe the darkest objects in the universe directly. Gravitational waves also pass through matter almost completely unimpeded. Light can be blocked by dust clouds, scattered by gas, absorbed by intervening galaxies. Gravitational waves just sail right through. They carry pristine information about their sources, undistorted by anything in their path. This matters because the early universe was opaque to light. For the first 380,000 years after the Big Bang, the cosmos was a hot, dense plasma that scattered photons like fog scatters headlight beams. We cannot see anything before that era with electromagnetic radiation. But gravitational waves from that epoch would have traveled through unimpeded if we could detect them, and future detectors might be sensitive enough. We could observe the universe in its infancy, perhaps even moments after the Big Bang itself. We could watch the first black holes form. We could trace the mergers that built the supermassive black holes at the centers of galaxies. We could detect signals from cosmic strings, if they exist, or from phase transitions in the early universe. We could test general relativity at the very edge of its domain, where gravity is so strong that quantum effects might become important. LIGO opened a window. Future detectors will open a door. The detection of gravitational waves also confirmed something profound about general relativity. Einstein's equations, written in 1915, predicted exactly what LIGO observed in 2015. The waveform, the frequency evolution, the amplitude, all match the calculations to exquisite precision. After 100 years, general relativity remains unbroken. But physicists keep testing. Every detection is a new opportunity to look for deviations from Einstein's predictions. So far, none have been found. General relativity has passed every test we have thrown at it, but the search continues. If we ever find a discrepancy, it would revolutionize physics. In January 2025, LIGO detected an event designated GW250114. It was described as the clearest gravitational wave signal ever detected, with a signal-to-noise ratio of 80. The two black holes that merged had masses of about 85 and 66 solar masses, producing a final black hole of about 140 solar masses. That detection was special for several reasons. The exceptional signal strength allowed researchers to observe the ring-down phase in unprecedented detail. They detected multiple quasi-normal mode frequencies, the different tones of the new black hole ringing down to stability. This confirmed a prediction of general relativity called the no-hair theorem, which says that the properties of a final black hole depend only on its mass and spin, nothing else. Even more remarkably, the data confirms Stephen Hawking's area theorem at greater than 5 sigma significance. Hawking proved in 1971 that the total surface area of black hole event horizons can never decrease, a kind of second law of thermodynamics for black holes. The initial black holes in GW250114 had a combined surface area of roughly 240,000 square kilometers, about the size of the United Kingdom or the state of Oregon. The final black hole had an area of roughly 400,000 square kilometers, about the size of California or Sweden. Despite all the energy lost to gravitational waves, the total area increased, exactly as Hawking predicted. Kip Thorne commented that if Hawking was still alive, he would have reveled in seeing his theorem confirmed so dramatically. Here is something that astonishes me every time I think about it. The machines that detected gravitational waves were designed and built by the same species that, just a few thousand years ago, was still figuring out that the Earth goes around the Sun and not the other way around. The same species that invented the wheel maybe 6,000 years ago, writing maybe 5,000 years ago, the scientific method maybe 400 years ago. In the span of a few centuries, we went from not knowing that other galaxies existed to detecting the collisions of black holes in galaxies billions of light years away. We went from not knowing what stars are made of to forging the same elements in our laboratories. We went from thinking the universe was static to watching it expand and evolve in real time. And now, we have learned to hear the universe speak. The gravitational waves LIGO detects carry information from the most extreme environments in the cosmos. Regions where gravity is so strong that time nearly stops. Regions where space itself is twisted into knots. Regions that are fundamentally inaccessible to any other means of observation. Every detection teaches us something new about the population of black holes in the universe, about how they form and merge, about the violent deaths of massive stars. About the nature of gravity itself, we have built instruments capable of measuring distances smaller than the nucleus of an atom. We have heard the universe whisper secrets it has kept for billions of years. We have opened a new window on creation, and this is just the beginning. The gravitational wave astronomy of today is like the optical astronomy of Galileo's time. We are using the first crude telescopes, seeing things no one has seen before, not quite understanding what we are looking at. The gravitational wave astronomy of the future will be like the Hubble Space Telescope, seeing deeper and clearer than we can currently imagine. Future detectors will observe black hole mergers from the edge of the observable universe. They will watch supermassive black holes spiral together over thousands of years. They will detect gravitational waves from the Big Bang itself, a cosmic background of ripples left over from the birth of everything. We will map the population of black holes across cosmic time. We will understand how the first stars formed and died. We will test the limits of general relativity and perhaps find where it breaks down. We will look for gravitational waves from sources we have not yet imagined, signals that will surprise us and reshape our understanding of the cosmos. All of this because one September morning in 2015, a whisper from the universe reached Earth. A whisper that had traveled 1.3 billion years. A whisper that changed everything. Marco Drago saw it first. A signal on a screen. Numbers that did not make sense until they made perfect sense. The chirp of two black holes becoming one, heard for the first time by human instruments. And now we listen every day, every hour, waiting for the next whisper, the next secret the universe wants to share. The cosmos is speaking. We have finally learned to hear. But I want to take you deeper into the details, because the devil, as they say, is in the details. And the details of how LIGO actually works are almost as astonishing as what it detected. Let us talk about noise. Everything in the universe vibrates. The ground shakes from earthquakes happening thousands of miles away. Traffic on nearby highways creates subtle tremors. Ocean waves crashing on distant beaches generate seismic waves that propagate through the entire Earth. Even the thermal motion of molecules, the random jiggling of atoms at any temperature above absolute zero, creates vibrations. LIGO has to measure displacements smaller than 1,000th the width of a proton while sitting on a planet that never stops shaking. This is like trying to hear a pin drop during a rock concert, except the rock concert is the entire Earth and the pin is being dropped on another continent. The first line of defense is location. LIGO Livingston is in rural Louisiana, surrounded by forests. LIGO Hanford is on a decommissioned nuclear reservation in the desert of eastern Washington. Both sites are far from major highways, train lines, and industrial facilities. But even in these isolated locations, the ground never stops moving. The second line of defense is the suspension system I mentioned earlier. The quadruple pendulum is an engineering masterpiece. Each stage filters out vibrations at different frequencies. The combination provides isolation that improves as frequency increases, roughly as the inverse eighth power of frequency above a few hertz. At 10 hertz, ground motion is reduced by a factor of about 100 billion before it reaches the mirrors. But even that is not enough. LIGO also uses active isolation. Sensors detect ground motion, and actuators apply counterforces to cancel it out. This works particularly well at low frequencies, where passive isolation is less effective. The combination of active and passive isolation allows LIGO to operate in the presence of continuous microseismic noise from ocean waves thousands of miles away. The third major noise source is thermal noise. Even at room temperature, molecules vibrate. In a solid object like a mirror, this appears as a kind of random wobbling of the surface. If the surface is your measuring device, that wobbling is noise. LIGO fights thermal noise in several ways. The mirrors are massive, 40 kilograms each. More mass means more inertia, which reduces the effect of thermal fluctuations. The mirrors are made of ultra-pure fused silica, a material with very low mechanical losses. In physics jargon, it has a high quality factor, meaning it does not absorb and release energy efficiently. This concentrates the thermal noise into narrow frequency bands, leaving the regions between those bands quieter. The suspension fibers are also made of fused silica for the same reason. The optical coatings on the mirror surfaces are a major source of thermal noise, and enormous effort has gone into developing coatings that reflect nearly all the light while adding minimal noise. At the highest frequencies, quantum noise dominates. This comes from two sources. First, photon shot noise. Light is made of discrete particles called photons, and the random arrival times of individual photons creates noise in the measurement. More photons means more averaging and less noise, which is why LIGO uses such powerful lasers. Second, radiation pressure noise. Photons carry momentum, and when they bounce off the mirrors, they give the mirrors tiny kicks. With hundreds of thousands of watts circulating in the arm cavities, the cumulative momentum transfer is not negligible. The random fluctuations in photon number create random forces on the mirrors. Here is the subtle thing. Increasing laser power reduces shot noise, but increases radiation pressure noise. There is a trade-off. At any given frequency, there is an optimal power that minimizes the total quantum noise. This is called the standard quantum limit. But LIGO has found a way to beat it. Beginning in the third observing run, LIGO began injecting squeezed light into the interferometer. Squeezed states are a quantum mechanical trick. The Heisenberg uncertainty principle says you cannot know both the amplitude and phase of a light wave with perfect precision. But it does not say the uncertainty has to be equal in both. Squeezed light sacrifices precision in one variable to gain it in the other. By injecting squeezed light with reduced phase uncertainty, LIGO can measure the tiny phase shifts caused by gravitational waves more precisely than would otherwise be possible. This technique, which earned its developers the 2005 Nobel Prize in Physics, gave LIGO a roughly 2 to 6 decibel improvement in sensitivity, depending on frequency. Future detectors will use even more aggressive squeezing and may employ quantum non-demolition techniques to push sensitivity well below the standard quantum limit. Let me tell you more about what happens when two black holes actually collide, because the physics is mind-bending. Black holes are not solid objects. They are regions of space-time where gravity is so strong that nothing, not even light, can escape. The boundary of a black hole is called the event horizon. Cross it, and you are gone forever, falling inexorably toward the singularity at the center. When two black holes orbit each other, they do not just move through space, they drag space-time with them. This effect, called frame dragging, was predicted by general relativity and has been confirmed by satellite experiments. Near a spinning black hole, space itself rotates. As two black holes spiral together, their gravitational fields interact in complex ways. The space-time between them becomes violently distorted. Computer simulations of these mergers require solving Einstein's equations in full generality, a task so difficult that it was not accomplished until 2005. In the final moments before merger, the black holes are orbiting each other at a significant fraction of the speed of light. At GW 150-914, the final orbital velocity was about 150,000 kilometers per second, roughly half the speed of light. The orbital period was a few milliseconds. Each black hole was completing hundreds of orbits per second. Then the event horizons touch. This is not like two balls colliding. It is more like two drops of water merging. The horizons blend together, forming a single, highly distorted event horizon. This merged horizon is lumpy, asymmetric, nothing like the perfect sphere or oblate spheroid of an isolated black hole. But general relativity does not allow that asymmetry to persist. The no-hair theorem says a black hole is completely characterized by just three properties: its mass, its angular momentum or spin, and its electric charge. Any other information, any bumps or wiggles or irregularities, must be radiated away. That radiation is the ring down. The newly formed black hole vibrates like a struck bell, shedding its irregularities as gravitational waves. The frequencies and damping times of these vibrations are called quasi-normal modes, and they depend only on the mass and spin of the final black hole. Measuring the ring down is incredibly valuable. It provides an independent check on the masses determined from the in-spiral phase. It tests whether the final object really is a black hole, as predicted by general relativity. Any deviation from the expected quasi-normal modes would be a sign of new physics. In GW 150-914, the ring down was too weak to measure precisely. But in larger, louder events like GW 190-521 and GW 250-114, the ring down has been studied in detail. The results confirm general relativity's predictions with impressive precision. Let me talk about the other side of the detection equation, the humans. The LIGO scientific collaboration includes over 1,300 scientists from more than 100 institutions in 20 countries. It takes that many people because building and operating these detectors requires expertise in laser physics, quantum optics, mechanical engineering, material science, seismology, computer science, and general relativity. No single person, no single institution could do this alone. The data analysis is its own enormous effort. LIGO generates about a gigabyte of data per second. Most of that is instrumental channels monitoring the health of the detectors. But even the gravitational wave channel produces far more data than humans can examine manually. Automated pipelines search the data for signals using matched filtering, a technique that compares the data against a library of predicted waveforms. LIGO's template bank contains millions of waveforms covering the parameter space of expected signals. When the data matches a template well, that is a candidate detection. But matched filtering only works if you have templates. For signals that do not match the expected patterns, other methods are needed. Burst searches look for short transients without assuming a specific waveform. Continuous wave searches look for persistent signals from rotating neutron stars. Stochastic searches look for a background of unresolved sources. Each search produces candidates that must be vetted. Real gravitational waves should appear in all detectors with consistent timing and consistent waveforms. They should not coincide with known instrumental glitches or environmental disturbances. The vetting process is painstaking and involves human judgment as well as automated checks. Once a confident detection is made, parameter estimation begins. This is the process of inferring the properties of the source, the masses, spins, distances, and sky locations from the gravitational wave signal. It involves running millions of simulations and comparing them to the data using Bayesian statistical methods. A single event can require days of computation on large computing clusters. The results are published in catalogs. The third gravitational wave transient catalog, GWTC. 3. Covered events through the end of the third observing run in March 2000 and included 90 events. The fourth observing run has added hundreds more. Each event is a data point in the emerging science of black hole demographics. Before LIGO, we knew very little about the population of stellar mass black holes. We knew they existed because some were in X-ray binary systems, slowly consuming companion stars. But those represented a biased sample, only the black holes close enough and in the right configurations to produce X-rays. LIGO sees black holes through their mergers, a completely different selection effect. And what LIGO has found has been surprising. First, black holes are heavier than expected. Many of the black holes LIGO has detected have masses in the 30 to 50 solar mass range, larger than most astronomers predicted. This suggests that massive stars can collapse more directly into black holes than previously thought, without losing as much mass in the process. Second, some black holes are spinning surprisingly slowly. Theory predicted that black holes formed from collapsing stars should be spinning rapidly. Many of the LIGO detections show moderate or low spins. This is still not fully understood. Third, some black holes are in the so-called pair instability mass gap. Stars with helium cores above about 65 solar masses are expected to explode completely as pair instability supernovae, leaving nothing behind. Stars with helium cores above about 130 solar masses collapse directly into black holes. In between, stellar mass black holes should not form. Yet LIGO has detected black holes in this forbidden range. GW190521 involved black holes of about 85 and 66 solar masses, producing a final black hole of about 142 solar masses, squarely in the mass gap. This might indicate that these black holes formed through previous mergers, hierarchical assembly in dense stellar environments, or it might mean our understanding of stellar evolution is incomplete. These puzzles drive ongoing research. Every detection adds another clue. The population is coming into focus, but the picture is still blurry and full of surprises. Let me return to the neutron star merger of 2017, because its significance cannot be overstated. When LIGO and Virgo detected GW170-817, they immediately sent out an alert to the astronomical community. The sky localization from the gravitational wave signal alone was poor, a region of about 30 square degrees. But that was enough for telescopes to start searching. The Fermi gamma ray burst, arriving just 1.7 seconds after the merger, narrowed things down considerably. Fermi's localization was also imprecise, but the overlap of the gravitational wave and gamma ray error regions pointed to a smaller patch of sky. The SWOPE telescope at Las Campanas Observatory in Chile was one of the first to find the optical counterpart, less than 11 hours after the gravitational wave detection. The source was in NGC 4993, a lenticular galaxy about 40 megaparsecs away. It was a new point of light that had not been there before. Over the following days and weeks, the source evolved in a way never before observed. It started bright and blue, then faded and reddened. The spectrum revealed heavy elements, lanthanides and actinides, products of R-process nuclear synthesis. This was the kilonova, the radioactive glow of freshly forged, heavy elements. The theoretical prediction of kilonovae dated back decades, but no one had ever seen one. Now, we were watching heavy elements being created in real time, the cosmic forge at work. The optical observations alone would have been a major discovery. Combined with the gravitational waves, they were revolutionary. The gravitational wave signal told us the masses of the neutron stars, about 1.4 and 1.2 solar masses. It told us the distance, about 40 megaparsecs. It told us the orbital inclination, roughly face-on. The gamma-ray burst told us that a relativistic jet formed, as expected in short gamma-ray burst models. The slight delay between merger and burst, 1.7 seconds, constrained models of jet formation and propagation. The kilonova told us how much material was ejected, roughly a few hundredths of a solar mass. It told us the composition, rich in heavy neutron-rich elements. It told us the velocity of the ejector, about 1/5 the speed of light. X-ray and radio observations, emerging over the following weeks, traced the interaction of the jet with the surrounding medium. They revealed that the jet was structured narrower and faster in the center, wider and slower at the edges. Altogether, this was the most complete picture ever assembled of a cosmic explosion. Gravitational waves caught the moment of merger. Gamma rays caught the jet formation. Optical light caught the kilonova. X-rays and radio caught the afterglow. Multi-messenger astronomy had arrived. The other great result from GW170, 817, was the measurement of the Hubble constant. Because the gravitational wave signal gives an independent measure of distance, a standard siren, it provides a completely new way to measure cosmic expansion. The Hubble constant has been a source of controversy in cosmology. Measurements from the cosmic microwave background, extrapolated forward using our best cosmological model, give a value of about 67 kilometers per second per megaparsec. Measurements from nearby supernovae and Cepheid variable stars give about 73. The discrepancy is statistically significant and has resisted resolution. Gravitational wave measurements offer a third approach, free of the systematic uncertainties that might affect either of the other methods. The initial estimate from GW170, 817, was about 70 kilometers per second per megaparsec, with large uncertainties. As more neutron star mergers are detected, the precision will improve. Eventually, gravitational wave standard sirens may resolve the Hubble tension or deepen the mystery. I want to spend a moment on the engineering that makes all this possible, because it represents some of the most precise engineering ever achieved by humans. The lasers used in LIGO are not off-the-shelf equipment. They are custom-built ND-YAG lasers, operating at a wavelength of 1.064 micrometers. In the near-infrared, the initial laser produces about 200 watts, but this is amplified and cleaned through multiple stages. The laser must be incredibly stable in both frequency and intensity. Any fluctuations would appear as noise in the gravitational wave measurement. Frequency stabilization is achieved using the Pound-Drever-Hall technique I mentioned earlier, locking the laser to a reference cavity with stability better than 1 Hz out of 300 trillion Hz. Intensity stabilization uses feedback systems that detect and correct fluctuations in real time. The beam splitter at the heart of the interferometer is a 50-50 mirror that divides the laser beam equally between the two arms. It is made of the same ultra-pure fused silica as the test masses and must be optically perfect. Power recycling is another clever technique LIGO uses. Most of the laser light that enters the interferometer gets reflected back toward the laser. Rather than wasted, a power recycling mirror reflects it back in, building up the power inside the system. This effectively multiplies the laser power by a factor of about 40. Signal recycling does something similar for the gravitational wave signal. A mirror at the output port sends some of the signal back into the interferometer, enhancing the response at certain frequencies. The position of this mirror can be adjusted to tune the detector's sensitivity curve. The vacuum system is a marvel in itself. The 4-kilometer beam tubes are made of spiral welded stainless steel in sections about 20 meters long, joined by welds that must be vacuum tight. The entire system is baked out to remove adsorbed water and other contaminants. The ultimate pressure is about 100 billionth of atmospheric pressure, achieved after weeks of pumping. At that pressure, a typical molecule will travel about 400 kilometers before colliding with another molecule. The beam tubes are only 4 kilometers long, so most molecules bounce off the walls before hitting anything. The rare collisions that do occur scatter laser light and create noise, which is why the vacuum must be so extreme. The seismic isolation system combines multiple technologies. At the lowest level, each test mass chamber sits on a hydraulic external pre-isolator that provides about 10-fold isolation. Above that, an active 2-stage isolation platform uses sensors and actuators to cancel ground motion, achieving about 3,000-fold isolation at 10 Hz. Finally, the quadruple pendulum provides passive isolation that improves rapidly with frequency. The test mass chambers themselves are among the cleanest environments ever created. Particle contamination would scatter laser light, so the assembly of the optics is done in clean rooms with stringent protocols. The mirrors are never touched by human hands. They are suspended from their fused silica fibers using a process that takes days to complete. Each mirror is also an active element. Tiny magnets are bonded to the back, allowing actuators to apply forces for alignment and control. These actuators must themselves be incredibly quiet, adding negligible noise while providing the necessary degrees of freedom. The control system that keeps everything aligned and resonating is enormously complex. There are hundreds of feedback loops operating simultaneously, each one stabilizing some degree of freedom. If one loop goes unstable, it can knock others out of alignment, causing the whole detector to lose lock. Maintaining lock for days or weeks at a time requires constant monitoring and occasional human intervention. When a gravitational wave passes through, it is detected as a differential change in the lengths of the two arms. One arm gets slightly longer, while the other gets slightly shorter. This shows up as a phase shift in the recombined laser beam, which is converted to an intensity change at the output port. The output is a photodetector, a device that converts light into electrical current. The current is digitized and recorded at 16,384 samples per second, about 16 kilohertz. This determines the upper frequency limit for gravitational wave detection, around 7 or 8 kilohertz. The data is time-stamped using GPS receivers to better than 1 microsecond accuracy. This is essential for comparing signals between detectors and for correlating with astronomical observations. All of this technology, this symphony of lasers and mirrors and pendulums and vacuums, exists to measure a change in length smaller than the nucleus of an atom. It is absurd. It should be impossible. And yet, it works. I cannot help but marvel at what this says about human capability. We are small creatures on a tiny planet orbiting an ordinary star in a typical galaxy. The universe is vast and mostly empty and completely indifferent to our existence. And yet, we have reached out across that vastness and detected the most violent events in the cosmos. We have built machines that can feel the trembling of space-time itself, we have found a way to listen to the music of the spheres, not metaphorically, but literally. The gravitational waves detected in 2015 had been traveling through the universe since before complex life existed on Earth. They passed through billions of galaxies on their journey, and at the end, they stretched and squeezed a few kilograms of fused silica by a distance smaller than anything we had ever measured before. We caught them. We heard them. We understood them. There is something profound about that. It speaks to the power of human curiosity, the patience of scientific inquiry, the cumulative nature of knowledge building. Einstein made his prediction in 1916. Weiss wrote his paper in 1972. The first detection came in 2015. Nearly a century of work, thousands of scientists, billions of dollars, all to hear a whisper that lasted 0.2 of a second. Was it worth it? I think about what we have learned. We know now that black holes merge. We have measured their masses and spins. We have seen how they form new black holes. We have confirmed general relativity in the strong field regime. We have watched neutron stars forge heavy elements. We have measured the expansion of the universe in a new way. And we are just getting started. The detections will keep coming, hundreds per year, then thousands. The detectors will improve, seeing farther and more clearly. New observatories will open new frequency bands. We will trace the history of black holes across cosmic time. We will test general relativity in ever more extreme conditions. We may find something that breaks our theories and forces us to think again. I think about the scientists who made this possible. Rainer Weiss, who designed the detector and spent decades perfecting it. Kip Thorne, who understood what signals to look for and championed the project when others doubted. Barish, who transformed a troubled collaboration into a successful experiment. Ronald Drever, who invented key technologies but did not live to see the Nobel Prize. Joseph Weber, who had the vision even if his apparatus was not up to the task. I think about the 1,300 members of the LIGO scientific collaboration, the hundreds of engineers and technicians who built and maintain the detectors, the computing specialists who process the data, the theorists who calculate the waveforms. No single person could have done this. It took a global community working together across decades. And I think about what comes next, the Einstein telescope, with its 10-kilometer arms underground. Cosmic Explorer, with 40-kilometer arms stretching across the landscape. LISA, with spacecraft millions of kilometers apart, listening to a completely different symphony. We will observe the mergers of supermassive black holes at the centers of galaxies. We will watch stellar objects spiral into those giants over thousands of years. We will detect thousands of compact binaries in our own galaxy, a foreground of gravitational waves that LISA will have to see through to find the distant signals. Perhaps we will find something completely unexpected. The history of astronomy is full of surprises. When Galileo pointed his telescope at Jupiter, he did not expect to find moons. When Penzias and Wilson pointed their radio antenna at the sky, they did not expect to find the cosmic microwave background. When LIGO turned on, the first thing it heard was two black holes merging, an event whose rate was at the upper end of theoretical predictions. The universe has a habit of being more interesting than we imagined. So what happens when two black holes collide? Now you know. Space-time itself trembles. A chirp of gravitational waves races outward at the speed of light. 1 billion years later, it passes through our planet and stretches a laser beam by less than the width of a proton. An Italian postdoc in Germany sees it on a screen. the world changes. We built a machine that can hear the universe, and the universe had something to say. That morning in September 2015, when Marco Drago first saw the signal, he did not know he was witnessing history. It took months to confirm, months of painstaking analysis and careful checking. But eventually, there was no doubt. We had done it. After a century of dreaming and half a century of trying, we had finally detected gravitational waves. Einstein was wrong when he said it could never be done. He was right about so much else, about the nature of space and time, about the existence of gravitational waves themselves. But he underestimated human ingenuity. He did not foresee the lasers and the quantum optics and the isolation systems that would make detection possible. Perhaps that is the lesson. The universe is stranger and more wonderful than any one mind can imagine. It takes generations of scientists building on each other's work to tease out its secrets. And even then, there is always more to learn. The gravitational waves keep coming. Every few days now, LIGO and its partners detect another merger. Each one adds to our knowledge. Each one tests our theories. Each one is a message from the cosmos, a story written in the language of bending space-time. We are learning to read that language. We are learning to hear the music. And we are only just beginning. There is one more thing I want to tell you about, because it reveals something important about how science actually works. In the months between the first detection and the public announcement, the LIGO collaboration had to keep the secret. More than 1,000 scientists knew that gravitational waves had been detected, and not one of them leaked it. In an age of social media and instant communication, that level of discipline is remarkable. Why the secrecy? Because premature announcement could have been catastrophic. Remember Joseph Weber? He announced detections that could not be replicated, and it nearly destroyed the field. The LIGO team was determined not to make the same mistake, so they checked everything. Multiple analysis pipelines examined the data independently. Hardware experts verified that no equipment malfunction could have produced the signal. The blind injection team confirmed that no fake signal had been inserted. Theorists compared the observed waveform to numerical relativity simulations. Statisticians calculated the probability of a noise fluctuation producing such a signal by chance. Every possible source of error was investigated. The team argued, debated, and questioned every aspect of the analysis. When the announcement finally came in February 2016, they were as certain as scientists can be that the detection was real. This is how science is supposed to work, not with dramatic eureka moments broadcast live, but with careful, methodical verification. The excitement is there, burning underneath, but it is tempered by the knowledge that being wrong would be worse than being late. The confirmation of the discovery came from subsequent detections. GW151226 arrived on December 26, 2015, while the collaboration was still analyzing the first event. It was weaker, from smaller black holes, but it was clearly another gravitational wave. Then came more events in the second and third observing runs. Each one added to the evidence. Each one made the case stronger. By the time the Nobel Prize was announced, there was no serious doubt left in the physics community. LIGO had done what it set out to do. But the story of gravitational wave detection is not just a story of success. It is also a story of failure, of wrong turns and dead ends, of ideas that did not pan out. Before laser interferometers, there were resonant bars. Weber's bars were followed by cryogenic bars cooled to a fraction of a degree above absolute zero to reduce thermal noise. Groups in Italy, Australia, and the United States built increasingly sophisticated versions through the 1980s and 90s. None detected gravitational waves. The signals were simply too weak, and the bars were not sensitive enough. There were also proposed space missions that never flew. The Big Bang Observer would have detected gravitational waves from the very early universe. It was deemed too ambitious and too expensive. Various configurations of space-based interferometers were studied and abandoned before LISA's design was finalized. There were false alarms. In February 2016, just days after the announcement of GW150914, there was a burst of excitement about a potential detection from a ground-based detector in Japan. It turned out to be noise. There were technical setbacks. Initial LIGO struggled with problems that kept it from reaching design sensitivity. A light baffle fell and had to be retrieved. Scattered light created unexpected noise. The detector spent years in commissioning mode, not yet ready for science observations. Even advanced LIGO had problems. Scattered light from imperfect mirror surfaces created noise that limited sensitivity. The input mode cleaner, an optical cavity that filters the laser beam, was difficult to keep aligned. The control systems had to be retuned repeatedly as the detector improved. Each problem was eventually solved, but the solutions took time and effort. The path from concept to detection was not straight. It wound through technical difficulties and funding uncertainties and personality conflicts and scientific debates. It took longer than anyone initially expected. This is the reality of big science. The public sees the triumphant announcements, the Nobel Prizes, the headlines. They do not see the years of frustration, the experiments that did not work, the grants that were rejected, the papers that were criticized. For every success, there are many failures, and even the successes take far longer than planned. LIGO was proposed in the 1980s. It was funded in the 90s. Initial LIGO ran from 2002 to 2010 without detecting anything. Advanced LIGO was proposed, built, and commissioned over another 5 years. The first detection came in 2015, about 30 years after the initial proposal. 30 years. Entire careers were spent on this project. Some of the scientists who started it did not live to see it succeed. Others retired before the first detection. The younger scientists who celebrated in 2016 were standing on the shoulders of those who came before, many of whom never got the recognition they deserved. This is the intergenerational nature of scientific progress. We build on what others started. We leave foundations for others to finish. The questions we ask today may not be answered in our lifetimes, but they will be answered eventually by those who come after. I think about what it must have been like for Rainer Weiss in the early years. He wrote that paper in 1972, laying out the entire concept. He knew it could work in principle, but he also knew it would take technology that did not yet exist, funding that was not yet available, and time measured in decades. He kept going anyway. He built prototypes. He recruited students. He pushed the technology forward, inch by inch. When LIGO was proposed, he fought for it. When it was criticized, he defended it. When it was funded, he helped build it. When it struggled, he helped fix it. In 2015, Weiss was 83 years old. He had spent more than 40 years working toward a goal that many thought was impossible, and he lived to see it achieved. He was in the room when David Wrightsey announced the detection. He gave interviews, wrote articles, accepted prizes. He saw his life's work validated. Not everyone was so fortunate. Ronald Drever was in a care facility, his mind clouded by dementia. He had been forced out of the project he helped create, his difficult personality making continued collaboration impossible. He contributed some of the key technologies that made detection possible, but he was not there to celebrate. Drever died in March 2017. 7 months later, the Nobel Prize was announced. If he had lived 7 more months, he might have been included, or he might not have been, since Nobel rules limit the prize to 3 recipients, and Barish's contribution to the project's success was arguably greater than Drever's. We will never know. The rules are what they are. The prize went to Weiss, Thorne, and Barish. Drever's name appears in the scientific papers, in the technical documentation, in the memories of those who worked with him, but it does not appear on the Nobel citation. Science is full of such tragedies. The contributions of individuals get lost in the collective achievement. The wrong people get credit. The right people are forgotten. History is written by those who survive long enough to tell the story. But the gravitational waves do not care who discovered them. They keep propagating through the universe, stretching and squeezing space, regardless of who is listening. They are a feature of reality itself, existing whether we detect them or not. That is what makes science different from other human endeavors. The truths we uncover are not dependent on us. Einstein's equations were true before Einstein wrote them down. Gravitational waves existed before we detected them. The universe does what it does whether we understand it or not. Our role is to bear witness, to pay attention, to build instruments that can reveal what is already there. The glory of the discovery belongs not to any individual scientist, but to humanity as a whole. We did this together. We figured it out. The signal that arrived on September 14th, 2015 was not addressed to anyone in particular. It was broadcast in all directions, an ever-expanding sphere of rippling space-time. It passed through countless galaxies, through interstellar space, through our solar system. It happened to hit Earth at exactly the moment when we had finally built instruments capable of detecting it. Was that luck? Was it destiny? Or was it simply probability, the inevitable result of gravitational waves being common and detection being possible? We may never know how many gravitational waves passed through Earth in the centuries and millennia before LIGO. They left no trace, no evidence of their passage. They stretched and squeezed the planet by amounts too small to measure, too brief to notice. The universe was singing, but no one was listening. Now we are listening. Every day, every hour, the data streams in from detectors around the world. Automated systems scan for signals. Human analysts review the candidates. When a detection is confirmed, alerts go out to astronomers, to theorists, to the public. The universe is speaking. We are writing down what it says, and the messages keep coming. Black holes merging, neutron stars colliding, maybe someday supernovae exploding, pulsars wobbling, cosmic strings snapping. Maybe someday signals we cannot yet imagine, from sources we have not yet theorized. Gravitational wave astronomy is in its infancy. We have learned to hear, but we are still learning to understand. The signals we detect today are the brightest and loudest. The cosmic shouts. The future will bring sensitivity to softer sounds, the cosmic whispers. When the Einstein telescope turns on, it will detect black hole mergers from the edge of the observable universe. When LISA launches, it will hear supermassive black holes dancing around each other, for thousands of years before they merge. When Cosmic Explorer comes online, the detection rate will soar into the hundreds of thousands per year. We will map the population of black holes across cosmic time. We will watch galaxies merge and their central black holes spiral together. We will test general relativity in conditions that make current observations look gentle by comparison. And we may find something that breaks everything we think we know. An unexpected signal, an impossible source, a deviation from Einstein's predictions that reveals new physics. That is the excitement of exploration. You do not know what you will find until you find it. The universe is bigger and stranger than our theories predict. It always has been. Every time we build a better telescope or a more sensitive detector, we discover things we did not expect. Gravitational wave detection is the newest way of seeing the cosmos. It joins optical telescopes, radio telescopes, X-ray satellites, neutrino detectors. Each method reveals different aspects of the universe. Together, they paint a picture that no single method could provide. The picture is incomplete. It will always be incomplete. The universe is too vast, too complex, too strange for us to ever fully understand. But we keep trying. We keep building better instruments. We keep asking better questions. We keep pushing back the boundaries of ignorance. That is what it means to be human, to wonder, to question, to seek answers even when the answers seem impossibly far away, to build machines that can measure the unmeasurable and hear the unhearable. On September 14th, 2015, we heard the universe for the first time. The sound was two black holes becoming one. A chirp lasting 0.2 of a second, created 1.3 billion years ago. It was worth the wait. It was worth the decades of work, the billions of dollars, the careers dedicated to a goal that many thought impossible. It was worth every setback, every failure, every argument, every compromise. Because now we know that space-time can ripple. We know that black holes merge. We know that we can build machines sensitive enough to detect the faintest vibrations of reality itself. We know that the universe is speaking, and we have finally learned to listen. But let me leave you with one final thought, because I think it captures something essential about what we have accomplished. The gravitational waves detected by LIGO traveled for 1.3 billion years. During that journey, they passed through the voids between galaxy clusters, through the halos of countless galaxies, through the interstellar medium of our own Milky Way. They encountered nothing that could stop them, nothing that could absorb them, nothing that could significantly alter their message. Light cannot do that. Light gets absorbed by dust, scattered by gas, blocked by opaque objects. The cosmic microwave background is the oldest light we can see, and it comes from only 380,000 years after the Big Bang. Before that, the universe was too hot and dense. A plasma that scattered photons like fog scatters headlight beams, but gravitational waves pass through everything. They traveled unimpeded from the moment they were created, carrying pristine information about their source. When we detect them, we are seeing the universe as it truly was, not as it appeared after being filtered through intervening matter. This is why gravitational wave astronomy is so revolutionary. It is not just another way of observing the cosmos. It is a fundamentally different kind of observation. Electromagnetic radiation tells us about matter, about charged particles and their interactions. Gravitational waves tell us about mass and energy, about the bending and warping of space-time itself. We have spent 400 years improving our ability to see electromagnetic radiation. We started with Galileo's telescope. then added radio, infrared, ultraviolet, X-rays, gamma rays. Each new wavelength revealed something previously hidden, but all of it was still electromagnetic, still light in the broadest sense. Gravitational waves are not light. They are not electromagnetic at all. They are a completely new medium, a new channel of information, a new sense that we have developed as a species. It is as if we had spent our entire existence deaf, communicating only through sight, and suddenly we developed ears. The world sounds different than it looks. We can hear things we could never see. The universe has a voice, and we are only now learning to understand it. What will we hear in the coming decades? What secrets is the universe keeping that we will uncover? What surprises await us in the data streams of future detectors? No one knows. That is the beauty of exploration. You go into the unknown precisely because it is unknown. You build the instrument because you want to see what it will show you. You turn it on and you wait. And if you are lucky, the universe rewards your patience with something astonishing. September 14th, 2015 was one of those moments. A signal arrived from the distant cosmos, a message sent before complex life existed on Earth. And we were there to receive it. We were ready. After a century of work, after decades of building and testing and failing and trying again, we were finally ready. The universe had been speaking all along. We just were not listening. Now we are. The detectors hum. The lasers shine. The mirrors hang suspended in their vacuum chambers, waiting for the next ripple in space-time to pass through. Somewhere out there, black holes are spiraling together. Neutron stars are about to collide. Supernovae are exploding in distant galaxies. The gravitational waves from these events are already on their way. They are propagating through the cosmos at the speed of light, carrying information about the most violent events in the universe. Some of them will reach Earth tomorrow. Some will arrive in 1,000,000 years. We will be ready, not us personally perhaps, but humanity. The project of understanding the universe will continue. Future generations will build on what we have started, just as we built on what came before. The instruments will improve, the detectors will multiply, the science will advance, and the universe will keep sending its messages, ripples in the fabric of space-time, stories written in the language of gravity. All we have to do is keep listening.